Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this live session of solid mechanics course. So the idea is of course to communicate directly with the students. If you have any question, please type it in the message box and I will be able to see what question you have and we will try to address your question as much as possible. And I'm also here with my TA, Darius Barreto, who is doing PhD under me. So I'm looking forward to your questions. Okay. Okay, so the first question that we have is about notation for the stress components. So in the class, we all have learned about stress component sigma xy, isn't it? Where we said that y denotes the plane normal. On what plane is this component acting? Whereas x, this denotes the direction. Of traction component. Okay. So sigma xy basically means the traction on y plane in the direction of x. Alright? So that's E1 for example. E1 if it is in the x direction. So traction on y plane in the x direction. So that's our convention. But in most of the books of linear elasticity or strength of materials, you will see the notation is somewhat opposite. They say that sigma xy is such that the first one is for the plane normal. Okay, the first one is for the plane normal and second one is for the direction of traction component. So it's actually the opposite. Now, why did we follow a different notation than what people are doing? You see, first of all, these are two different conventions and one need not be strict about these conventions. You can choose any convention you want. Okay? Then the second thing is, we have done this using tensors. Alright? So you can recall, for example, that the stress tensor sigma, we wrote it as traction Ti, tensor product Ei, isn't it? And it was a summation for I equal to 1 to 3. So when you write this in the matrix form, then you actually see that sigma ij is Tj dot Ei. So if we use this definition of the tensors and write things in the matrix form, then indeed J here denotes the plane normal and I denotes the direction of the traction, in which direction we are measuring the traction component. Okay? You know, you can also use different definition for denoting tensors and then finally come up with a formula which will be concurrent with the other definition that is on the right hand side. So as I told you, it's all about definition. But one very strong argument to use what we have been doing is that, when you learn advanced topics of elasticity, like advanced solid mechanics, you learn about what's called Piola-Kirchhoff stress tensors. This is Cauchy stress tensor. There you learn about Piola-Kirchhoff stress tensor. Okay? For example, P, and you have two types of Piola-Kirchhoff. So let's talk about first Piola-Kirchhoff stress tensor. And there you will actually see that in all the books, the components of the Piola-Kirchhoff stress tensor, if we denote by P, small I, superscript, and J, then indeed the first component here, the first subscript I, that indeed denotes the direction, and the second one denotes the plane normal, which is what we have done in this course also. Okay, so in nonlinear elasticity, almost everywhere the first Piola-Kirchhoff components have the same convention that we did for the Cauchy stress tensor. So that's another motivation for why we used different convention for Cauchy stress tensor. Alright, but finally, bottom line, you can use either of the conventions. The choice is yours. You just have to be clear about what's the meaning of first one, what's the meaning of second one, and then you be consistent with that particular convention everywhere. Alright? Okay. Okay, then the next question that we have, many of you have asked how to derive the stress equilibrium equation in spherical coordinate system. Okay, so how to derive a stress equilibrium equation in a spherical coordinate system. So you can recall that we actually derived this equation in Cartesian coordinate system, and then the equation that we got was del sigma xx over del x plus del tau xy over del y plus del tau xz over del z plus body force in the x direction is equal to density times acceleration in the x direction. And then we had two more equations. So that's for the Cartesian coordinate system, isn't it? And this derivation wasn't so difficult. But then we worked out the derivation in cylindrical coordinate system, and you can recall that the derivation was really difficult, isn't it? For example, the equation in the radial direction, that turned out to be del sigma rr over del r plus 1 over r del tau theta r over del theta plus del tau, del tau rz over del z. So these are the usual terms, but then you also had extra term, sigma rr minus sigma theta theta over r, right? Plus the body force in radial direction, and that's equal to density times acceleration in the radial direction. Likewise, you also had equation in the theta direction and then in the z direction. But the derivation was quite tedious, isn't it? And actually the derivation for the spherical coordinate system is also tedious. But you know, there is a nice, easy way to derive these equations. It turns out the stress equilibrium equation you can write in tensor form in the following way. So the tensor form of equation. So that turns out to be divergence of the stress tensor. So we all are familiar with the divergence, right? So you have to take the divergence of the stress tensor plus the body force vector B equal to density times acceleration A. So that's a compact notation, a compact form of stress equilibrium equation, and it's a tensor form. So you simply have to expand this compact form, or you have to write this component form in Cartesian coordinate system, or in cylindrical coordinate system, or in a spherical coordinate system. And then you will obtain the equations in the related coordinate system. Okay? For example, if we have to do it in the Cartesian coordinate system, then you have to write down the divergence in the Cartesian coordinate system. Okay? So the first one, for example, this becomes del by del x of sigma dot EI plus del by del y of sigma dot E2. So, okay, the first one is E1 plus del by del z dot sigma dot E3. Okay, and sigma also you will write in the Cartesian coordinate system. So sigma, for example, would be summation over ij sigma ij EI tensor product EJ, where E1 is the E1 direction, E2 is along Y direction, and E3 is along Z direction. Okay, and you simply take this derivatives del by del x of sigma, del by del y of sigma, and del by del z of sigma, expand it, and you will exactly get the equations for the Cartesian coordinate system. Likewise, when you had to do in the cylindrical coordinate system, that also you can do mathematically. You just have to write down this divergence of sigma in cylindrical coordinate system. So the divergence operator, first of all, in cylindrical coordinate system is del by del r of sigma dot product ER plus 1 over r del by del theta of sigma dot product E theta, okay, plus del by del z of sigma dot product Ez. So that's the definition of divergence in the cylindrical coordinate system. And then you have to also expand your sigma in cylindrical coordinate system. So sigma would then be again double summation ij sigma ij ei tensor product eg. But here E1, E2, E3 are not along x, y, z. They are along r, theta and z. So E1, for example, is ER, E2 is E theta, and E3 is EZ. Okay, and then when you take the derivative with respect to r, theta and z, you have to remember that the basis vectors here, E1, E2, E3, which are along ER, E theta, Ez, they are also changing when you change your theta coordinate, right? So that means when you work out this derivative, del by del theta of sigma, then you have to make sure that you also take the derivative of ER and E theta with respect to theta. Okay? Alright, so I hope you guys are getting it. As I told you, if you have any question, please write down your question in the message box. Okay? So we have some more question here. Okay, another question that was asked by some of you is about the symmetry of stress matrix or symmetry of stress tensor. So you can recall that in our lecture, when we did the angular momentum balance, the stress tensor then turned out to be symmetric. So whether the body is accelerating, whether you have body force acting or not acting, body is rotating, in all the cases, stress is always symmetric. So for the domain of the course, stress is always symmetric. But there are advanced theories. For example, we have what's called Coursera theory of elasticity, in which the unknowns, when you solve the deformation problem, the unknown is not just the displacement of every point of the body, but every point of the body has got some rotational variable also associated with it. So every point in the body has got displacement u as well as a rotation variable associated with it. The way to visualize this physically is that there could be a body which has got some microstructure in it. For example, liquid crystals, they have got some, or let's say you have a magnetizable body which has magnetic dipoles in it. So magnetic dipoles has got some direction. So think of a body and you have magnetic dipoles embedded in the body everywhere. So in that case, you not only talk about the displacement of every point of the body, but you also want to know what's the orientation of magnetic dipole at every point in the body. Okay? So in addition to displacement, the rotation is also an unknown at every point in the body. And it turns out in such theory, you not only have body force, which is acting at every point in the body, but you also have what's called body couple. So body couple is something that we never talked about in this class. But in advanced theories, while dealing with liquid crystals, for example, or with magnetic dipoles, magnetizable bodies, magnetizable materials, you also need to talk about magnetic dipoles. And there you also get body couple at every point in the body. Okay? So you see, per unit volume you have got body couple. So when you do the volume integration of this body couple, you get the net moment due to the body couple. So with the presence of body couple, when you work out the angular momentum balance, then you will see that the stress tensor is no more symmetric. So for such theories, which is an advanced theory of course, stress tensor is not symmetric. The Cauchy stress tensor does not turn out to be symmetric. But otherwise, for the domain of this course, which is the first course to solid mechanics, we always think that the stress matrix is symmetric or stress tensor is symmetric. Okay? Alright, let's see what more question we have. Okay, so I'll just make this remark here. In advanced theory of elasticity, where we deal with, for example, liquid crystals or magnetizable materials, then we also want to know the orientation of the microstructure. So orientation of the microstructure, which is magnetic dipole in case of magnetizable material, is also an unknown. And there we also have body couple. It's quite interesting. And due to that, the stress tensor, basically the Cauchy stress tensor, is no more symmetric. Okay? Alright, so the next question that we have is, we want to know about the difference between what's called infinitesimal strain tensor and Lagrangian strain tensor. So this is something actually we have also done in the class. So in the class, you can recall, we came across this expression isn't it? And then we said that the last term here, so this is quadratic in displacement gradient. And for linear elasticity, displacement gradients are assumed to be very, very small. So del U1 by del X1, for example, would be of the order of 0.1 or 0.01. So when you take its quadratic combination, for example, del U1 by del X1 into del U1 by del X2, that's going to be even smaller. Therefore, in linear elasticity, we neglect this quadratic term and we only retain the linear terms in displacement. So what remains, that's called small strain tensor or infinitesimal strain tensor. Whereas if we don't neglect anything, if we keep everything, even the quadratic terms, so then we have what's called finite strain tensor or Lagrangian strain tensor. So in the advanced solid mechanics courses, where we also talk about large deformation, okay, so where we also talk about large deformation, we would have to even retain the quadratic term, and that's called finite strain tensor or Lagrangian strain tensor. Okay, all right. So Lagrangian strain tensor which is also called the finite strain tensor. So this retains even the quadratic term. Okay, whereas the infinitesimal strain tensor, it only keeps the linear terms in displacement. Okay, let's see what more question we are getting. So okay, there's another very interesting question about beam theory. There are different variants of beam theory, and we have learned about two of them. The most basic one, that's the Euler-Bernoulli beam theory, and then slightly advanced Timoshenko beam theory. But even these two theories do not handle all possibilities. There are approximations in Timoshenko beam theory also. One of them is that we neglect axial stretch. For example, think of solving this beam problem. Suppose we have this beam which is clamped at one end, but at the other end it is held by a rigid pole. Alright? So this is a collar. So it's a frictionless collar. So the beam can move up and down freely. There is no friction. But the collar is such that it's not going to allow the rotation at this end. So due to the collar, there will be no rotation. Okay? So can you think of solving this beam problem, let's say using Timoshenko beam theory? So we'll first write down the equations of Timoshenko beam theory. So that's EI d theta by dx is equal to bending moment, and then dy by dx minus theta is equal to shear force V over kGa. Correct? Let us suppose we are applying a force here also, some shear force F. So of course the first goal is to get the shear force and bending moment along the beam, right? So we'll have to draw the free body diagram of a segment of the beam, isn't it? So what will be the reaction from the pole on the beam? You see this, first of all, you are applying a force F on the beam. So there is a force F acting here. Then the beam is not allowed to rotate due to collar. So that means the pole is going to exert some reaction moment also. You see, whenever there is no rotation, that means there has to be some reaction moment. You can recall the table. So there is a reaction moment which is an unknown. Let's call it ML, and that's an unknown. Likewise, you see there is no axial displacement allowed at this end because it is adhered to the rigid pole, and this pole cannot move axially, isn't it? This pole cannot move axially. So even this end of the beam cannot move axially. So that means the pole must exert a force in the axial direction on the beam, right? So you have a reaction force even in the axial direction, and that's also an unknown. So this is an unknown, and ML is also an unknown. Whereas on the other end, you have shear force V, then bending moment M, and then you also have axial force. Now when we do force balance, this simply tells us that Vx is equal to F. What about the moment balance? Let's do moment balance about this point. So we have minus M of x plus ML plus F into L minus x, isn't it? Because this length is L minus x. But then we have some more term. You see, now the axial force PL is also going to induce some moment, and that's equal to PL times YL, the deflection at the tip, YL, minus the deflection at x, which is Y of x, and we simply denote it by Y. So this implies your moment M of x is actually ML plus F into L minus x plus PL into YL minus Y. So if we plug these in our equation, we get EI d theta by dx, that's equal to M, which is ML plus F into L minus x plus PL into YL minus Y, right? And the second one is dy by dx minus theta is equal to V, which is F itself divided by kGA, right? So how many unknowns are present in this equation right now? So you have ML as unknown, PL is also an unknown, then you have two integrating constants, right? Because it's two first order equations, so you get two integrating constants plus two integrating constants. So total 4 unknowns. So we will need 4 boundary conditions. And do we have 4 boundary conditions here? So let's see whether we have 4 boundary conditions. So at the clamped end, no rotation, so theta of 0 is equal to 0. No displacement, so y of 0 is equal to 0. Whereas on the other end, theta of L is also equal to 0. Do we have any other boundary condition? We don't have any other boundary condition. So we have only 3 boundary conditions but 4 unknowns. So we can't solve this problem. And why is this the case? So can you guess why is this the case? It's because we are not modeling axial deformation of the beam here. Although we have axial force, but we are not modeling axial deformation of the beam. If we also had axial displacement as an unknown, then we could have written that the axial displacement, let's call it by U, at L is equal to 0, because that end is not allowed to displace axially, right? And so we get 4 boundary conditions for the 4 unknowns. But none of the Euler-Bernoulli or Timoshenko beam theory allows axial deformation So we need theory which also allows axial deformation in order to solve these problems, right? Likewise, you see in both the theories, what can you see about the magnitude of rotation? See, in Euler-Bernoulli theory, we said that dy by dx, the slope of the center line, that's equal to theta, the cross-section rotation, because center line tangent and the cross-section normal both were aligned. But dy by dx is not really the angle. Dy by dx gives you tan of theta, isn't it? So tan inverse dy by dx should be equal to theta. But we approximated tan inverse of dy by dx by dy by dx. So that happens only when dy by dx is very, very small, isn't it? So Euler-Bernoulli beam theory works only when the rotation is small. Likewise, even Timoshenko beam theory. So in Timoshenko beam theory, we have dy by dx minus theta equal to v by kGa, right? But actually it should be tan inverse dy by dx minus theta equal to v by kGa. But again, we are saying that angle is very small, so we replace tan inverse dy by dx by just dy by dx. So none of the two theories actually allows for large rotation of the cross section. Okay? So none of the two theories allows for large rotation of the cross section. But you know, there are deformations where the rotation can be very significant. Just think of this cable. You know, look at this cable. Its cylinder body. You apply a twist to this cable. Can you see how much is the bending and twisting? There is a lot of bending and twisting. What about the cross-section rotation? See, initially they are all horizontal. The cross-section normal, each cross-section, each of its normal is horizontal, right? Let's think of this deformation. Look at the cross-section over here. Where is the cross-section normal? It's vertical. So it has rotated by 90 degrees. Look at this cross-section. The cross-section normal is pointing backward. So it rotates by 180 degrees. Now look at this cross-section here. This is also pointing in the same direction, but it actually rotated by 360 degrees. And for such rotations, you can of course never say that tan inverse dy by dx is equal to dy by dx, right? But these deformations are physical, you see. So when you want to model such deformations, you have to forget about Euler-Bernoulli or Timoshenko beam theories. And there are advanced non-linear beam theories which you have to learn. For example, you can talk of Kirchhoff rod theory or Kossarad rod theory. Okay, so these theories allow large cross-sectional rotation. Okay. So let's see if we have got some more questions. Okay, another question that is coming is the relationship between stress and strain. And why we took it to be linear. So actually it's not linear. Taking linearity is just an approximation. And that's something we deal with in this first course. We want to keep things linear. That's why this course is also called linear elasticity. So stress could be non-linearly dependent on strain. It could have quadratic dependence or cubic dependence 4 times, or it could be logarithmic. So it need not be linear. Okay? But any function, you can always do its Taylor's expansion, and then you will write it in polynomial. The first term will be constant, then the linear term, then higher order term. And if the strain is very small, you can always neglect the higher order term and only retain the terms up to linear order. And that's what we are doing in this course. Okay, so when we say that stress and strain are linear, this holds only when strain is small enough. If strain becomes large, then we have to talk about non-linear stress-strain relationship. In fact, then we also have to talk about non-linear strain-displacement relationship, isn't it? Because we then have to talk about finite strain tensor when the strain is large. We won't neglect the quadratic combination of displacement gradient then. So in case of finite deformation theory, we have two kinds of non-linearity. Okay, so we can write that here. In finite deformation theory, we have two types of nonlinearity. So the number one is nonlinear stress-strain relation. And number two, we have nonlinear strain displacement relation. This first nonlinearity is also called material nonlinearity. Whereas the second one, that's called geometric nonlinearity. Because the second one is more from kinematics, isn't it? Therefore it's called geometric nonlinearity. First one is more about the material behavior, stress-strain relationship. That's why it's called material nonlinearity. And in finite deformation theory, we have both the nonlinearities. Whereas in linear elasticity, we neglect nonlinearity of both the things and only keep the terms up to linear order. Okay? So that answers your question about why we keep a stress-strain relationship to be linear in this course. Alright? So I guess we have no further question. If you have some question, please write your message. And you can, of course, so we are not really having any more question now. So you can, of course, write me an email asking a question. Okay. So we can close the live session now. Thank you. कहाँ से बंद करना है? स्टॉप करना है. हाँ, हो गया.